Hi folks, this video continues with the Unit 4 series. We're going to be looking at extrusive volcanic features at this stage. We're looking at volcanoes as we know them at this point now. These are the extrusive features, the ones that come to the surface. And we're going to be looking at three tectonic areas where these features form. Convergent plate boundaries, divergent plate boundaries, and hotspots, all of which have slightly different features, some similar to each other and some similar to intrusive features. If we start with the convergent plate boundary, this has got some similar features to the intrusive volcanic formations. The reason for this being that if you remember from the intrusive features, it could be that a pluton of magma was generated from the melting of the oceanic plate, Cinder oceanic plate, as it's subducted beneath the continental plate, which is mainly made of Sial. So the magma rises up, and as before, magma loses some of its Cinder down towards the bottom of the plate. But it doesn't lose as much this time. And the magma rises faster. The reason for this is, at this trench, where the plates are being subducted one underneath the other, water is mixing in with the magma. Now this lowers the melting point. It makes the magma much more viscous, which means it flows better. So there's less Cinder that's left behind, and there is more energy to get the magma up to the surface. So it doesn't cool as quickly as it's rising up, because it's still got a fair bit of density to it. It's dense, but it's more viscous. So it's hot, it's rising up, it's staying hot, and it cuts right up to the surface and creates a volcanic cone on the surface. Now, depending on how far that's had to travel through the crust, it may have lost more of its Cinder. It may have picked up more silica as it's gone, but it stayed hot and viscous because of the addition of water. Once it gets to the surface though, and it extrudes, gets onto the surface and comes out as lava, that water vapour is lost and you're left with the magma, which could be very high silica content. So you often get quite andesitic or rhyolitic magmas at convergent plate boundaries. They've been able to travel up because it's been mixed with water. That's made it less viscous and it's allowed it to reach the top. When it gets to the top, it is still a very much silica heavy magma. Now once it reaches the surface, that magma cools very quickly. In an intrusive feature, the magma cools very slowly, hence why you get granites with large crystals. Crystals tend to be a lot smaller, so you get different types of rock. See your rock charts, which I gave to you as a resource to find out which types of rock have formed. And the types of volcanoes that form tend to be relatively conical in shape, cone-shaped volcanoes. They may be either made up of layers of ash, layers of lava, layers of ash, layers of lava. These are called composite cone volcanoes. The composite cone, again, see the resource I gave you. Or it could just be ash and cinders, and that's called a cinder cone volcano. The reason for this is, the reason why they're not big lava flows very often. They tend to be more explosive, further up the explosivity scale, which is also in your resource, is that the magma is thicker. It's higher in silica content, so it tends to be thicker, and that means that it cools quicker when it's exposed to air, and it can form a plug in the vent. So what you get with a composite cone is you get a plug that forms, pressure builds up behind it, and then bang, the plug's blown out, ash goes everywhere, flies out, lands on the side of the volcano, followed by a layer of lava which can flow out the vent. So you get the ash, blows out, settles, but all that pressure that built up, there's still lava that's flowing behind it, and then it flows out and creates a lava layer. So you get explosion, ash, lava. The last bit of the lava will cool and form the next plug. So lava's coming up, it's cooled, it's plugged, it's up the gap, pressure builds again, bang, another explosion, ash, lava, and then the last bit of lava forms a plug. If the magma is even thicker and more rhyolitic, then you don't even get a lava flow, you just get explosions, because all the lava solidifies within the chamber and just blasts itself to pieces. And then so you just get cinders and ash and solid objects without really any significant lava flow. If you get right up to the top end of the rhyolitic scale, really high silica content, you get one of these volcanoes will have such a big plug and so much pressure builds behind it that it just blows the volcano to pieces, like Krakatoa did, and it leaves a caldera. Leaves a caldera behind. So that is the where you've had the most explosive form of explosion. And once the volcano has blown itself to pieces, you're unlikely to get big explosions after that. You might just get releases of gas. But that would have blown itself completely to pieces. So to recap, convergent boundaries, you've got quite silica heavy magma, but the water allows it to rise quicker, gets to the surface, forms a volcano, and because it's silica heavy, it creates cones. You can get these three different types: composite cones, cinder cones, or calderas. In terms of landforms, that's fine. But what about the rest of the country rock? Well, you could say the thicker the country rock that the magma has to travel through, the more silica heavy the magma is going to become, which means you're going to get those steeper cones and you're going to get more explosivity. Also, notice that as the magma is being generated at the point where the oceanic plate melts and it goes straight up, it's actually a fair way away from the plate boundary. So where you've got your trench, you have to go a few hundred kilometres back before you start getting volcanoes. And they will form a line all the way along the plate boundary. You get this in places like the Philippines. Pinatubo is a good example. So that kind of extra detail about where you'd find these in the context of the landscape is very important. Next up, we have divergent plate boundaries. Now, divergent plate boundaries, of course, they're moving apart from each other. You get a very different experience. The fact that the plates are pulling apart from each other, and they're generally oceanic plates, Sima plates, means that the lava has got very little distance, the magma has got very little distance to go through before it becomes lava. It only has to slide through the gaps as the plates crack apart. So it just has to slide up from the mantle through the asthenosphere, and then it just oozes out. Hasn't really got anywhere to go. And because there's very little resistance, it means it's still very high in magnesium, so there's a lot of Sima. It still stays very, very hot, and you get very basaltic lava. So it's very hot, very viscous, but it cools really quickly because generally it's underwater. So it just cools it straight away. Very, very small crystals formed. If it cools really rapidly, you can get obsidian, which is kind of glass-like. Or you can get basalt, very, very dense, teeny tiny crystals. But the magma remains very hot, and it flows out, and it creates, well, it barely creates much of a feature at all, actually, in some places, because it just runs over the top and creates these flows, just builds up a bit of a ridge. And that's why things like the Mid-Atlantic Ridge are ridge shape, is because the volcanoes have basically just added little bits of layer to the edge of the plate boundaries. So you get a ridge. Alternatively, if you're perhaps exposed to the air, you might get shield volcanoes. They look a bit like this. We'll come back to this side in a moment, but they look a bit like this, flat and wide. Iceland has a lot of them. Eyjafjallajökull is a classic example. And again, the magma is so hot that it just runs straight out, and it'll run for a large distance before it cools. So it creates these big flat shapes, compared to the thick magma and the ash, which can't flow as far. Think back to the idea of the silica content again. This is low silica. So thinking back to the custard analogy, it's like there's a lot less custard powder in there. Whereas it's like there's a lot more custard powder in here, making it thicker, won't flow as far. So in terms of features, we've got very hot viscous magma which just gets straight out and runs away to the sides. Same in the East African Rift Valley, actually. Greater context? Well, it's on the plate boundary. It's no distance back like you get with the convergent boundary. The magma is always very viscous, very basaltic, low silica. Sometimes, though, you will get slightly higher silica, and that will just create a kind of cracked black surface on top of the magma, rather than it just being red hot. Generally very viscous, very not very viscous at all, very runny. Next up we have hotspots, and a shield type volcano is one that shows up again at hotspots. Because hotspots tend to have quite basaltic lava. They are different though, they're a bit unusual. As you'll know from the first video that I did on the geology, there are convection currents at a divergent boundary in the mantle that move the plates apart, like so. And that pulls those plates apart. Now sometimes you get a convection current that just rises up for no apparent reason, generally underneath an oceanic plate. And that means that there's enough heat and enough force to cause magma to rise up through the asthenosphere and emerge on the surface of the plate. You don't really know why, does it? But it does. And it forms shield volcanoes, much like in Hawaii. And these shield volcanoes rise up out of the ocean and form islands, like Mauna Loa. And what happens is they form, and the plate keeps moving along. So once they form, they move along, and then they go extinct, because the plate's moved past the hotspot and just leaves the island. And what you get is you get these island arcs that form. So you get a series of islands, like Hawaii, that follow a plate movement. And if you imagined an ocean, they kind of look like this, as the plate moves round in that kind of direction, slightly tilted. And each time the plate moves across, the hotspot keeps providing magma and a new volcano forms. Because it's only going up through a cyma, oceanic crust plate, the magma remains very hot, still very dense, so it retains its heat, and that's why you get these shield volcanoes. It can flow very effectively. So the lava can flow very effectively because it's low silica. In terms of the context, hotspots create these arcs. As I said before, like Hawaii, they tend to be in the ocean. So Hawaii, the perfect example there, because you've got Mauna Loa, which is the active volcano, and you've got the wider context of the arc. Now all of these volcanic features cool quicker than intrusive features. So you get smaller crystals. The other thing to consider as well about this is that at the moment we sort of see all these volcanoes, but there's no reason why there might not be some plutons forming that we don't even know about at the moment. So we could have intrusive features forming that we just don't know about and will only be found in the future. So, to recap, we've got high silica lava, which creates high silica magma, which creates high silica lava at convergent boundaries, pointy cones. We have divergent boundaries with very flat cones. This is a result of the basaltic lava. And then we have hotspots, where we have basaltic lava and it forms island arcs, whereas this tends to form ridges. This will finally leave us with the next video, which will cover seismic landforms. And once we've done that, we can think about how we can put all this information into a report.